Hello everyone. So in this session we will discuss about the floating point representation. In the previous lesson we have discussed how normalization is going to be done with respect to floating point. Now in this lesson we will discuss about the need for biased exponent and how we are going to bias the exponent. So before getting into those details, we will just discuss that the floating point representation can be classified into two categories. One is called as single precision, another one is called as double precision. So in single precision, the floating point numbers will take 32 bits, out of which 1 bit is reserved for the sign bit and 8 bits is reserved for the exponent and then 23 bit for the fraction. So this is the format followed for single precision floating point numbers. Now coming to double precision floating point numbers, it occupies totally 64 bits, out of which as usual 1 bit will be consumed for the sign bit and 11 bit for the exponent, and 11 plus 1 12, 64 minus 12, the remaining 52 bits will be reserved for the fraction. So in general, in floating point representation we can adopt either to single precision or to double precision depending upon the requirement. Now if we just observe the three fields, we have the sign bit, only one sign bit. So obviously this sign bit has to be associated only with the fraction. So if the fraction is going to be negative sign, that is represented with 1 here, and the fraction is going to be positive, it is identified by 0. But coming to the exponent also can be positive and negative. In that case, we need one more bit reserved for representing the sign of the exponent. But actually there is no field available for representing the sign of the exponent. What it actually implies is that the exponent should be made positive. So the negative exponents have to be converted into a positive exponent. Then only we can ignore the sign bit for exponent. So how it is going to be done, that we will see. So now coming to this exponent, we have 8-bit exponent. So with 8-bit you can represent 2 power 8 symbols. So totally 256. Okay. And if I start from 0, it will be 0 to 255. So this all represents only positive exponent. We told the exponent can be both positive and negative. That means we have to allocate half the range with the negative numbers and half the range with positive number. So how that is going to be done? So 256 by 2, 256 by 2, which is nothing but 128. Okay. So 128 symbols should be in positive. So we will be having from 0 to 128, and here in the negative side we will just reduce it by 1, so we will be having minus 127. So minus 127 to 0 and then from 0 to 128, because we can't have totally, it is only 256. So this is going to be the range of numbers that can be represented with an 8-bit exponent including the negative value and the positive range. So if this is going to be the range, the exponent will be having negative sign, and this negative sign has to be stored somewhere in the format, but we don't have any provision to include the sign bit for the exponent. That means we have to convert this negative exponent also into positive. How can we convert that? So if conversion is nothing but I want to make this negative to 0. That means if I add 127 to this number, this minus 127 to plus 127 will become 0. And if I add 127 to 0, it will become 127. And if I add 127 to 128, then it will become 255. So somehow or other, this minus 127 to 128, this range of numbers in exponent is going to be converted to 0 to 255. How am I converting? Whatever may be the exponent, I am going to add 127 uniformly. So if I add 127, the lowest range will become 0 and 0 will become 127, and if it is the maximum value 128, if I add 127, it becomes 255. So with 0 to 255, I will be able to do all the operations. So in order to make or convert the negative exponent into positive, I am just adding one quantity, positive quantity, and this positive quantity is nothing but called bias. So the reason for adding the bias to the exponent is to make it positive, because we don't have any provision to represent the sign of the exponent. Now coming to this details, E, as I told, it can be in the range from 0 to 255, totally 256. Okay, and in that range, what they have told, this number 0, E equal to 0 and E equal to 255. So both the numbers are reserved for some special purpose. Okay, so E equal to 0, exponent equal to 0 is not always used, and similarly the last range 255 is also not used. So out of 256 symbols, I am not going to use 0 and 255. So we have only 254 symbols totally to be represented. So 1 to 254 only will be used, and this is going to be normalized for floating point numbers. So the bias value to be calculated for 8-bit representation is, it is going to be 127. So if I always add the exponent 127 to this minus 127, it will become positive. So uniformly this bias value is going to be added when we convert the biased exponent representation. And when we are processing the values, then because we have added extra bias here, that has to be subtracted to get the equivalent value. So the value of E will be always whatever is the value of E, that has to be converted and it has to be subtracted with 127 to get the original value. This representation is called as biased exponent representation. And we have discussed this bias exponent representation with single precision. The same concept can be extended to double precision. Now coming to double precision, if you just see the exponent, it is going to be 11 bits. So with 11 bits, you can represent 2 power 11 symbols. So the total range will be from 0 to 2047. And in this case, as usual, the 0 and the last range both will not be used. So totally we will be having, so these two symbols should not be included. So totally we will be having only 1 to 2046. Only these many symbols only will be represented. That's what given here. So E equal to 0 and E equal to 2047 are reserved for special purpose. We are not going to make use of it. So the range will become from 1 to 2046. And this range of exponent is only going to be used for normalizing the floating point numbers. Now how you will calculate the bias, as told here. So totally we have 2048 symbols. So total I just divide by 2 so that I will have half the part in the negative side and half the part in the positive side. So this is going to be 1024, 1024. Okay, and out of this 1024, the range, if it is going to be the negative range, what I will be having? I will be having minus 1023, then 0, and only in the positive side we will be having up to 1024. So this is going to be the range of numbers that is going to be dealt with 11-bit exponent. And if this is going to be the 11-bit exponent, all the negative exponent has to be converted into positive, so that we have to add the bias. So what is the bias value here? If I want to make minus 1023 to 0, I have to add 1023. So if I add 1023 to the negative extreme, it will become 0. And when I do something to one exponent, the same thing has to be applied for all the values. So if it is 0, I will be adding 1023 as a bias value. So I will be getting 1023 here. And the same will be also added with the largest value, that is a maximum value in the range. So what you will be getting? 1024 to plus 1023 with the bias value will be added. So you will be getting 2047. So from this what we are trying to say, the exponent which is in the range minus 1023 to 1024, that includes positive and negative value, has to be converted only to positive range, because we don't have any provision to store the sign bit in the exponent part. This sign bit is associated only with a fraction. So we don't have any sign bit for the exponent. For that purpose, we convert the negative sign to positive sign by adding the bias. If I add the bias value should be made uniform for all the values. So when I add bias 1023 for the entire range, the new range what I am going to get will be 0 to 2047. So that is what explained here. So the new range will be E will be become 0 to 2047, out of which the first value and the last value will not be used. It will be reserved for special purpose, and this bias will be added. Since we add the bias value when we store the exponent, while doing the calculation, we have to subtract the bias. Only then I will be getting the actual value. So the bias has to be subtracted, because earlier it has been added to convert the negative to positive. So during the calculation, I will be compensating it by subtracting the bias. So this completes the discussion of the biased exponent. So as far as floating point representation is concerned, you have to remember two important points. One is called as normalization, another one is called as biasing. So what I mean by normalization, other one is called as biasing. So the biasing concept comes into picture in order to convert the negative exponent into positive exponent, because we don't have provision to store the sign of the exponent. So we have to convert negative exponent to positive exponent. That can be done by adding the bias value. So the bias value is going to be decided based on the number of bits used for the exponent. If it is 8 bit, the bias value is going to be 127. Okay, if it is 16 bits, the bias value is going to be 1023. So if the 8-bit exponent representation, the bias value is going to be referred as 127. So how we have identified the bias value, I think I have calculated here. It will be clear to you. Then for 16-bit representation, the bias value expected to make it a positive exponent will be 1023. So like this, based on the exponent size, we are going to decide the bias. So convert the exponent into positive value by adding the bias. So since we have done this addition in the beginning, during the calculation we have to subtract the bias. So this point you have to keep it in mind when we are discussing about the floating point addition, subtraction, multiplication and division. So that's all about biasing. And coming to normalization, what we define in normalization, the floating point numbers always expected to have the significant as 1, and then we have the dot, then we will be having the fraction part, and then we have the base. Okay, then we have the power plus or minus e. So this plus or minus c is always converted to positive by means of biased exponent, and by normalization we always expect one non-zero digit to the left of the decimal point. Sorry, binary point or decimal point depending upon the number system. Always a 1 is expected to be there, and this one is not going to occupy any storage. By relaxing this condition, it is possible for us to extend the range. So there is no memory required for storing this one. So by default, all the fractions are supposed to be normalized. There is an example that if the number is going to be 0000, if you have a number 0, then this number, can it be biased or not? So all the floating point numbers except for 0 cannot be normalized. So the 0, if I search 0, I cannot search a 1 here. Only if there is a 1, I can bring that 1 to the integer portion. So except for 0, all the floating point numbers can be normalized, and by normalizing we keep at least one non-zero digit at the most, and at least one non-zero digit to the left of the decimal point. If I have this sort of representation, this is called as normalization. So in floating point representation, you have to be clear with two concepts. One is called as normalization, another one is called as biasing. Normalization is done to reduce the storage space required, and we always assume that there is a 1 to the left of the decimal point in binary point. And coming to biased exponent, the exponent should be always converted to positive. For that we have to find the bias value. To find the bias value, we should know the length of the exponent. Accordingly, we will generate the bias value. So this bias value will be always added to the floating point numbers in the initial stage, and so during the calculation we have to subtract the bias which have been already added in order to get the correct result. So this completes the representation of floating point numbers. In the next session we will discuss about how floating point numbers can be added, subtracted, multiplied and divided. Thank you.